Data structures interview questions. Okay, let's kick things off with the basics. What asterisk is asterisk a data structure? Simply put, it's how we organize information in our computer programs. Imagine your room. If you just tossed everything on the floor, finding anything would be a nightmare. Data structures are like that organized closet. They help us store and retrieve information quickly and efficiently. There are tons of different types: arrays, linked lists, stacks, queues. Each is designed for specific situations. Knowing these common structures will really level up your programming skills. Okay, let's talk about why data structures are so vital in programming. Basically, they're like the building blocks for organizing information. They determine how efficiently your programs work with that data. Without choosing the right structure, you could end up with slow code, wasted memory, and a really tough time maintaining it as things grow. Different data structures excel at different tasks. Think of a hash table being super speedy for looking things up versus a tree being great for sorting. Ultimately, understanding them leads to cleaner, faster, and more reliable software. Okay, let's talk about arrays and linked lists. Fundamental data structures. Arrays are like a perfectly organized row of boxes. Each box has a number, and you can quickly jump to any box using that number. That makes accessing elements by their index really fast. However, arrays have a fixed size, so if you need more space, it can be tricky. Linked lists, on the other hand, are like a chain. Each link points to the next. They are flexible because they can grow or shrink as needed, and inserting or deleting items is generally faster, especially if you know where you want to do it. But accessing an item in the middle requires traversing the entire list, which takes longer. Okay, let's talk about when linked lists make a better pick than arrays, particularly in interviews. Linked lists shine when it comes to adding or removing elements quickly. Arrays need to shift everything around when you insert something in the middle, which can be slow. With linked lists, you just change a few pointers much faster. They're also great if you don't know how many items you'll have beforehand. Arrays need a fixed size upfront. While arrays are super speedy for grabbing elements by their index, linked lists offer more flexibility in those situations. Okay, let's talk about stacks. A stack is a really simple data structure that operates on the principle of last in, first out, or LIFO for short. Imagine you're stacking plates. You always add a new plate to the top, and you always take a plate from the top. That's essentially how a stack works. We use two key operations: pushing, which adds an item to the top of the stack, and popping, which removes and returns the topmost item. You can also peek at the top element without removing it, and check if the stack is empty. It's a really useful structure for things like undo/redo functionality in applications or parsing expressions. Okay, let's talk about queues. A queue is a fundamental data structure that operates on the first in, first out principle. Think of it like a line at a store. New items are added to the back, and when you need something, you take it from the front. It's super useful for things like scheduling tasks or handling requests one after another, making them a key component of many algorithms. Okay, let's talk about queues. Think of them like a line. The first person in gets served first. We have several ways to build a queue. The simplest is an array-based queue, which can be efficient but might need shifting when adding or removing elements. Then there's a linked list queue. It offers more flexibility but uses more memory per item. Circular arrays are also popular because they avoid that shifting problem. And finally, we have priority queues, where items are served based on their importance. Choosing the right type depends on what you're doing and how often you need to add or remove elements. Okay, let's talk about priority queues. They're like a super organized way to manage things based on how important they are. Imagine a hospital. They need to treat the most urgent patients first, right? A priority queue does exactly that. It's an abstract data type where elements are kept in order of their priority, and you can always quickly get the one with the highest priority. They are often built using heaps, which is like a carefully organized tree structure, making it really efficient to find the most important item. Okay, let's talk about circular queues. Think of it like a regular queue, but with a twist. Instead of having to shift all the elements when you remove something from the front, a circular queue wraps around back to the beginning. It's essentially a fixed-size array that acts as if its end is connected to its start. This clever design avoids wasting space and makes it super efficient for adding and removing items frequently. Okay, let's talk about decks. A deck, short for double-ended queue, is a really handy data structure. Imagine you're managing tasks, some that need to be done first, and others that can come in later. A deck lets you add things to the front of the line, just like adding something to a queue, but it also lets you remove things from the back. It's like having two ends on your queue. It's based on the FIFO principle, first in, first out, but with the flexibility of being able to access both ends. You can add and remove items at either end efficiently, which makes it useful in a bunch of scenarios. Think about things like undo/redo functionality, implementing a buffer, or even managing a task queue where you might need to process jobs in different orders. Okay, let's talk about recursion. Recursion is basically a function calling itself. It's like those Russian nesting dolls. Every good recursive solution needs two key things: a base case, which tells the function when to stop calling itself, and a recursive step, where the function calls itself with slightly modified input until it hits that base case. Recursion is super useful when working with data structures like trees and graphs, because these structures are often defined in terms of themselves. For instance, a tree is made up of smaller subtrees. So, recursively exploring a tree is a very natural way to process its nodes. Okay, let's talk hash tables. Think of them as super efficient lookup systems. They store data in pairs, a key and its corresponding value. The secret sauce is the hashing function. It takes your key like a name or ID and spits out an index number, telling you exactly where to find that information within the table. Now, sometimes two different keys can accidentally produce the same index. That's called a collision. But don't worry, there are ways to handle collisions, like using linked lists or probing for another spot in the table. Because of this clever design, hash tables offer really fast access, typically just a single step, no matter how much data you have. Okay, let's talk about hash maps and hash sets. They are both super useful data structures for quickly finding things, but they do different jobs. A hash map is like a dictionary. You have keys that are unique, and each key points to a value. Think of it as storing information in pairs. Hash sets, on the other hand, just keep track of what's unique within them, like a list of items where you only care if something is already present. They don't store any extra data alongside those elements. Both are really fast at looking things up, but they're optimized for different tasks. Understanding this difference is key when choosing the right tool for your problem. Okay, so hash tables are super fast, but they can run into problems when multiple keys map to the same spot. That's called a collision. There are two main ways we deal with these. The first is separate chaining, where each slot in our table points to a linked list. All the colliding items just hang out there. Alternatively, we can use open addressing techniques. This means if there's a collision, we try to find another empty spot in the table. We've got linear probing. It's simple but can lead to clustering, quadratic probing, which helps with that, and double hashing, which is generally the best option for avoiding those clusters. The best choice really depends on how full your table gets. Okay, let's talk about binary trees. Think of them like a family tree. The root is at the top, and branches extend out to the left or right. Each node holds some information, and it can have up to 2 children. We have a root node, which doesn't have a parent, then nodes branching off to the left or right. They come in different shapes too, like perfectly balanced trees where every level is full, or skewed ones that all point in one direction. They're really useful for organizing and searching data efficiently. You'll encounter them quite often in interviews. Okay, let's talk about binary search trees. Think of them like organized family trees, but instead of relatives, we have numbers or data. A BST is a special type of tree where each node can only have 0 or 2 children left and right. The really important thing is that all the values in the left side of any node are smaller than the value itself, and all the values in the right side are bigger. This structure makes searching, adding new items, and deleting things much faster than just a random collection of data. Okay, let's talk about the difference between binary trees and binary search trees. A binary tree is like any standard tree. Each node can have at most 2 children. There aren't any rules about how those children are arranged. Now, a binary search tree is a special asterisk kind of binary tree. It's organized in a really specific way. The value of a node is always smaller than its left child and larger than its right child. This ordering lets us do super fast searches, insertions, and deletions much more efficient than a regular binary tree. Okay, let's talk about balanced trees. A standard binary tree can get really wonky as you add more data. Think of it like a really long chain. Searching through it takes forever. So, what's the solution? Well, a balanced tree is one where all branches are roughly the same size. This keeps the height relatively small and ensures that operations like searching, adding, or removing things happen efficiently, generally in logarithmic time, which is much faster than on. Okay, let's talk about AVL trees. These are really cool binary search trees that automatically keep themselves balanced. Unlike a regular tree where the branches can get super messy, an AVL tree ensures that the height difference between its left and right sides never goes over 1. They do this using rotations. Basically, they twist and turn the tree to maintain this balance after inserting or deleting elements. Each node also remembers its own height, which helps them figure out if a rotation is needed. So, if you see an AVL tree in an interview question, remember that it's all about keeping things organized and efficient. Okay, let's talk about B trees. They're like super organized trees used a lot in databases and file systems. Unlike regular binary search trees that only have 2 children per node, B trees can hold many keys and pointers to multiple child nodes. This makes them really good at balancing themselves as you add or remove data, which helps keep searching, inserting, and deleting things super fast like logarithmic time. Essentially, they're designed for efficiency when dealing with large amounts of information. Okay, so let's talk about heaps. They're a super handy data structure that's all about organizing elements based on priority. Imagine it like a family tree where the oldest person is always at the top. That's the basic idea of a heap. We have 2 main types: min heaps, where the smallest element is at the root, and max heaps, where the largest element is at the root. Heaps are really useful when you need to quickly find either the minimum or maximum value in a collection, and they're built around efficient insertion and deletion operations. Okay, so heaps are really useful for managing data where you need to quickly access either the smallest or the largest item. A min heap is exactly what it sounds like. It keeps its root node as the smallest element. Think of it like a priority queue where the highest priority task always comes first. Conversely, a max heap does the opposite. Its root is always the largest element. This makes it ideal for things like finding the maximum value in a set quickly. The key difference lies in how they maintain their ordering. Min heaps prioritize smaller values, and max heaps prioritize larger ones. Remember the heap property that each node's value is less than or equal to its children in a min heap or greater than or equal to its children in a max heap. Okay, let's talk about tries. They are often called prefix trees, and they are a really clever data structure for storing words. Imagine building a word letter by letter. Each branch of the tree represents one possible next letter. The root starts empty, then as you add letters, you create branches for each character. If a user types cat, we trace the path CAT. When we're done, a final node would be marked to indicate that cat is a valid word. Tries are fantastic for things like autocomplete suggestions and spell check because finding all words starting with a specific prefix is super quick. Okay, let's talk about graphs. They are a really important concept when you're prepping for data structures interviews. Basically, a graph is just a way to represent relationships between things. Think of it like a map of connections. It has nodes, which are the individual items in your network, and edges that show how those items are connected. These edges can be directed, meaning they go one way, or undirected, meaning you can travel back and forth. Sometimes, these connections also have weights associated with them, like distance between cities or cost of a route. There are different kinds of graphs too: directed, undirected, weighted, cyclic, acyclic. Really useful for modeling all sorts of real-world scenarios. Okay, let's talk about representing graphs in code. They're incredibly useful for modeling relationships between things. We have a few main ways to do this. First up is the adjacency matrix. Think of it like a grid where each cell indicates whether there's an edge connecting two vertices. It's great when you have lots of connections, but can use a lot of space if your graph isn't very dense. Then we have the adjacency list. Essentially, for each vertex, we make a list of all its directly connected neighbors. This is really efficient when dealing with sparse graphs, using less memory. Finally, there's the edge list. This just lists every connection between vertices in order. While not as common for direct graph manipulation, it can be handy when you're building your graphs from other data sources. It's important to consider whether your graph is dense or sparse to help you choose the best representation that will affect how much space you need. Okay, let's tackle the difference between directed and undirected graphs. They both show relationships between things. Think of them as nodes connected by edges. In an asterisk and directed asterisk graph, those connections are like two-way streets. If A is linked to B, B is also linked to A. It's a mutual connection. On the other hand, asterisk directed asterisk graph is like a one-way street. The link from A to B doesn't mean you can automatically go back from B to A, it's just in that specific direction. Understanding this difference is really important when you're working with graph algorithms. It impacts how you traverse and analyze the relationships. Let's talk about weighted graphs. Essentially, a graph is just a way to represent relationships between things like cities connected by roads. But often, we don't just care that two places are connected. We need to know how much it costs or takes time to get from one to the other. That's where weighted graphs come in. A weighted graph is a regular graph, but each connection, each edge has a number attached to it, called its weight. This way can represent anything from the distance between two cities to the cost of traveling on that road, or even the time it takes. They are represented using adjacency matrices or adjacency lists, which are pretty common ways to organize this information. Okay, let's talk about cycles in graphs. Basically, a cycle is like a loop. You start at one point and end up back where you started without ever retracing your steps. It's important to distinguish between a simple cycle, which doesn't repeat any vertices, and a self-loop, where a node just points back to itself. Cycles are really important in graph algorithms because they can cause problems if we aren't careful. Algorithms like DFS and BFS need to be able to detect cycles to work properly. Okay, let's dive into detecting cycles in graphs. A really common interview question. There are a couple of main ways to do this. Depth first search is a popular choice because it's relatively straightforward. The core idea is that if you're exploring a graph and you come back to a node you've already visited in the current path, that means there's a cycle. We use a visited array to keep track of nodes we've seen before, and crucially, our recursion stack. This is what really helps us identify cycles. It's like a stack of where we are in our current exploration. If we revisit a node that's already on the stack, boom, cycle detected. I'll show you a basic Java example to illustrate how it works. Remember, the algorithm iterates through each node and calls itself recursively to explore its neighbors. Okay, let's talk about depth first search and breadth first search, two really important graph traversal techniques. DFS is like going down a winding path. It dives deep into one branch before backing up and trying another. It often uses a stack to keep track of where it's been. DFS, on the other hand, explores everything at the current level before moving deeper. Think of it like checking your immediate neighbors first. It typically uses a queue for this purpose. The main difference is that DFS goes deep, while BFS goes wide. Understanding when to use each one is key to solving graph-related problems effectively. Okay, let's talk about DFS and BFS, two fundamental graph traversal algorithms. Both have a time complexity of OV plus E, meaning they visit every vertex and edge once. However, the space they use can differ significantly. DFS mainly uses recursion, so its space complexity is typically OV due to the call stack. Think of it like exploring a maze by going as far down one path before backtracking. It might take longer, but doesn't need to remember path simultaneously. BFS, on the other hand, utilizes a queue and explores level by level. This means it needs to store all visited nodes at each level, leading to a space complexity of OV in the worst case. So, if you're looking for the shortest path in an unweighted graph, BFS is your go-to. And if you need to check connectivity or find any path, DFS is often a more efficient choice. Okay, let's talk about dynamic arrays. Think of them like regular arrays but with a bit more flexibility. Instead of having a fixed size that you have to declare upfront, dynamic arrays can grow as they need to, no pre-planning required. They basically work by keeping track of how much space they're currently using and then grabbing more memory if they run out. It's great for situations where you don't know exactly how much data you'll be storing, especially when adding things to the end is a common operation. However, keep in mind that inserting or deleting items in the middle of the array can take longer because it involves shifting everything around. Okay, let's talk about linked lists. There are really two main types, singly and doubly. A singly linked list is like a chain, each link points only to the next one in line. It's simple and efficient for forward traversal. Now, a doubly linked list is similar, but it adds an extra pointer, linking each node back to its previous neighbor too. This means you can move both forwards and backwards through the list, which can be really helpful in certain situations. We'll also look at how much memory they use and where insertion/deletion are most efficient. Okay, let's talk about circular linked lists. They're essentially a linked list where the last node doesn't point to null. Instead, it circles all the way back to the beginning. Think of it like a loop. This is really handy in situations where you want to continually access elements without needing an explicit end signal, things like scheduling tasks or representing rotations. Each node has its regular data and also a pointer that loops back to the head, making traversal seamless. Okay, let's talk about linked lists. They're really cool because you don't need to decide how much space you'll need upfront. They grow and shrink as needed. Adding or removing elements in the middle is also usually quick, making them great when you're dealing with data that might change a lot. However, accessing specific items isn't as straightforward as it would be with an array. You have to follow links from the beginning. And because of that linking structure, they can use a little more memory and aren't always the most efficient for things like caching. Okay, let's talk about when you choose a stack over a queue. A stack follows the last in, first out rule, like a pile of plates where you always take the top one off first. This makes it perfect for things like ng/redo features in apps, or evaluating math expressions where you need to process items in reverse order. It's also used by compilers to manage function calls. Now, queues are completely different. They're first in, first out, just like a line at the grocery store. So, if you need to handle things in the order they arrive, a queue is probably what you want. Okay, let's talk about hash functions. They're super important when we're talking about efficiently storing and retrieving data. Basically, a hash function takes any piece of information you give it, whether it's a string or an object, and turns it into a unique number, kind of like a fingerprint. This number is the hash, and it's used to determine where that information will be stored in something called a hash table. It works by applying a mathematical formula to the input, generating an index for the table. Now, sometimes different pieces of data might generate the same hash. We call that a collision, and good hash tables have strategies for dealing with those situations without slowing things down too much. Okay, let's talk about what you need to know when it comes to working with binary search trees in an interview. There are 6 main operations that come up frequently: insertion, where we add new nodes while keeping the tree organized; deletion, which can be trickier because of how we have to handle different scenarios when removing a node; searching, obviously, to find if a value is present, finding the minimum and maximum values without scanning the entire tree; and then there's an order traversal, which gives us a sorted list of all the elements in the tree along with pre-order and post-order traversals. The most important thing to remember for all these operations is that binary search trees have a very specific property: every node's value must be smaller than its left child and greater than its right child. Understanding this property is key to solving many of these problems. Okay, let's talk about tree traversal. Essentially, it's how we systematically visit every single node in a tree. It's like having a map of a city and needing to make sure you hit every building. There are 3 main ways to do this: pre-order, in order, and post-order. Pre-order starts with the root, then goes left, then right. In order follows the left branch all the way down before visiting the root, and finally goes right. Post-order does the opposite, it travels down the right branch first, then the left, and then visits the root itself. Each order gives you a slightly different view of the tree's contents. Okay, let's talk about tree traversals. It's a really important concept in data structures and algorithms. We have three main ways to visit all the nodes in a binary tree: pre-order, in order, and post-order. Pre-order starts at the root, goes left, then right. Think of it like root, left, right, in order. On the other hand, visits the left subtree, then the root, then the right subtree, essentially left, root, right. Finally, post-order does a left traversal, then a right traversal, and asterisk, then asterisk visits the root. Each of these has different applications. Pre-order is useful for copying the tree, in order for sorting, and post-order can be handy when deleting nodes. Okay, let's talk about topological sorting, a really useful technique for working with directed acyclic graphs. Basically, it's all about figuring out the correct order to process nodes in a graph where some nodes depend on others. Think of it like building steps in a project. You need to complete the prerequisite steps first. We'll start by making sure there aren't any cycles. If there are, we can't sort them properly. Then, we calculate how many incoming edges each node has, called its in degree. Nodes with no incoming edges are our starting points. We then systematically process nodes from the queue, adding them to the order and updating the in degrees of their neighbors until everything is sorted. Okay, let's talk about Dijkstra's algorithm. It's a really important tool for finding the shortest path in a map-like situation. Basically, you have a bunch of cities connected by roads with distances between them. The algorithm starts at your starting city and systematically explores all the possible routes, always choosing the shortest one found so far. It keeps track of how far each city is from the start and updates those distances as it finds shorter paths to other cities. It's a greedy approach. It picks what seems best at each step without looking ahead too much, but that still guarantees you'll find the overall shortest route. Think of it like navigating a road network. You always take the next shortest turn. Let's talk about disjoint sets, also known as the union find data structure. It's a really clever way to manage groups of items, like finding out if two people are in the same club or team. Initially, each item is on its own, completely separate. Then, you can combine these group sets, the union part, merging sets together until everything's neatly organized. The core operations are find, which tells you what group a particular item belongs to, and union, which combines two groups into one. It's often implemented using a forest of trees, and techniques like path compression and union by rank dramatically speed up the process, making it super efficient for many problems. Okay, so when we're talking about data structures for interviews, it's really important to understand the difference between static and dynamic ones. Static data structures think of arrays of simple variables of a size that's set from the beginning, like building a wall with pre-cut bricks. They're great if you know exactly how much space you'll need, but they can't grow once built. Dynamic data structures, on the other hand, are more flexible. They're like Lego sets. You start small and add pieces as you go along. Linked lists and hash tables are prime examples. They adjust their size based on what's happening in your program. This makes them really useful when you don't know how much data you'll be handling, but it can sometimes come with a little bit of extra overhead. Okay, let's tackle building an LRU cache. The core idea is pretty simple. We need a way to quickly find data and also remember what we've accessed recently. To do this, we'll combine a hash map for super fast lookups with a W-linked list to keep track of the order in which things are used. Think of it like a shopping cart. You want to grab items quickly, the hash map, but if it gets full, you need to remove the oldest items first, the linked list. We'll use a hash map to store our key value pairs and the W-linked list to manage the order of access. The get method checks for an existing key in the hash map. If found, we return the value. If not, we return a default value. For put, if the key already exists, we update its value and move it to the head of the linked list. Otherwise, we create a new node, add it to the head, insert it into the hash map, and finally, When the cache is full, we remove the last element the least recently used from both the linked list and the hash map. Okay, let's dive into sparse matrices. Think of a huge spreadsheet, lots of empty cells. A sparse matrix is basically the same idea. It's a matrix where most of its entries are zero. Why do we care? Well, if you try to store every single element in a matrix, especially a really big one, you end up wasting tons of memory. It's much more efficient to just remember the non-zero values and their positions. That's what makes sparse matrices so valuable for things like image processing or recommendation systems, where data is often mostly empty. Okay, let's talk about Bloom filters. They're really clever little tools for efficiently checking if something might be in a set of data. Think of it like a super smart yes/no machine. Unlike a regular database lookup which guarantees an answer, a Bloom filter can sometimes give a yes even when the item isn't actually there. That's a false positive. It uses multiple hash functions to map each item to different bits in a large array. If all those bits are set, it says maybe this is here, but if even one bit is zero, then we know for sure it's not. Bloom filters are used everywhere, from speeding up database searches and preventing redundant network packets to helping spam filters and even caching things online. Okay, let's talk about segment trees. They are a really clever data structure for solving range queries efficiently. Basically, they build a tree where each node represents a chunk or segment of your original array. Each internal node stores the sum or min, max, whatever you need of the segments it covers. The leaves just hold individual values from the input array. When you want to find the sum between two indices, you don't have to check every single number in the array. Instead, you efficiently traverse this tree, only looking at the relevant parts that overlap with your desired range. This makes them incredibly helpful for problems where you need to repeatedly calculate aggregate values over different ranges, like finding the sum of a portion of an array. Okay, let's talk about how to pick the right data structure. It's a super important skill in interviews and beyond. First, you need to really understand what the problem is asking you to do. Think about asterisk. How asterisk you'll be using your data. Are you adding to it all the time? Are you just searching for specific items? Do the order of things matter? Then you can start looking at the properties of different data structures like arrays, linked lists, and hash tables and see which ones are best suited to handle those operations efficiently. Don't forget that there's often a trade-off involved. Sometimes you have to choose between speed and ease of implementation. Thank you for watching.